Good morning, everyone, and thank you for attending. Today's webinar is on theory, method development, and maintenance for the Hydra 2 AA, presented by Jeff Forsberg. We will be taking questions at the very end, but please submit your questions using the question feature, and we will address them at the end. Okay, Jeff, I'm handing it over to you.
Good morning, and thank you for attending. Today I'm going to discuss Hydra 2 AA. We will go over some theory, a quick review of the software, and then some method development. I'm going to discuss 4 methods: a intermediate trace range, an ultra trace range, a PPB that's conducive of EPA 245.1 type methodology, and then a high range that we will really push the instrument up to 1 milligram per liter. And then we'll end up with startup and shutdown, and then some basic maintenance of the system. So a little bit about Teledyne. So we develop instruments for most of your analytical needs. We provide customers with a choice of Mercury systems, and our Mercury analysis systems are based on the cold vapor atomic absorption spectroscopy, with or without gold enrichment. Our Hydra 2 Quick Trace Mercury product line and Quick Trace Mercury product lines are designed to cover a variety of techniques. But typically you need to have digested samples, and if they're digested properly, they'll meet all the stringent requirements of EPA methods and European norm methodologies. Some of our customers include environmental labs. We have systems in academia, petrochemical, food, mining, energy, pharmaceutical, nutraceutical, and water and wastewater, just to name a few of the customers that use our systems. So a little bit about atomic spectroscopy, cold vapor. It was introduced in 1968 by Hatch and others on the heels of the first atomic absorption spectroscopy. They developed a system that would take mercury after it was oxidized and reduce it to the ground state. This is your first hydride generation system. And they attached that to a flame AA system. They switched out the burner head and put a glass cell in there so the light could shine through the system. And the ground state atoms were transported up to the glass cell, and it was the absorbance was measured and detected by the system itself. And that quickly became the standard method. EPA adopted these techniques and became the standard method for water analysis, soil, and fish, just to name a few. A little bit about the Hydra AA CVAA system. It's an entry-level system. Our detection limits are less than 5 nanograms per liter. We have a usable range of 5 nanograms up to 1 milligram per liter, which we'll get into. And it can be quickly converted over to a thermal decomposition system, which suffices for EPA 7473. The Hydra AA is based on 245.1. Applicable methods typically require digestion unless you're reading just a pure standard. Post-digestion acidified samples with mercury present in the +2 valence state are introduced to the system with or without automation. The digest sample is then reduced by stannous chloride. Alternately, you can use sodium borohydride. If sometimes in Europe they still use this methodology. And the light source is at wavelength 253.65. Theory of operation. So an acidified sample with mercury in the +2, so it's post-digest, is introduced by a peristaltic pump, and a reducing agent is introduced parallel at the same time that the sample comes in. The reducing agent typically is a 10% stannous, and 10% hydrochloric acid. As I said, alternately you can use sodium or potassium borohydride. In the old method, 245-1 and 7470, they call out for stannous sulfate and sulfuric acid, and that's not recommended. It'll be cloudy white and a precipitate will form. So it's best to use the manufacturer's recommendation for the reducing agent. In our case, it's 10% stannous and 10% HCl. The sample and reagent streams join at the mixing T, and immediately the reaction takes place. So the stannous reduces acidified mercury to mercury 0 or elemental mercury while it's en route to the gas liquid separator. At the gas liquid separator, we bubble some gas through the system, and the elemental mercury is easily volatilized out of solution, and then it goes on to the naphthalene, and the waste stream is pumped down to the waste container. The gaseous stream of mercury vapor is then dried by the naphthalene. Naphthalene is a permapure dryer, and then it's directed to the atomic absorption system, the spectrometer. In the spectrometer, the gas is directed through two 5-inch cells for high sensitivity, low concentrations. But alternately, we can use a 1-inch cell for low sensitivity or high concentrations of the system. So the light from the lamp travels through the bottom cell, and then it's mirrored up to the top cell. This is how we achieve a 10-inch optical path. Then the signal is measured by the detector for integration time and the repeats of the number of programmed integrations for each sample. So as I stated, the normal configuration is a 5-inch cell, but if you want to utilize high concentrations, you need to reduce the sensitivity. So for that, we can plumb in the low cell, and that's going to give us about 10 times the level of concentration that we can hit with the system. Typical response in the long cell or the 10-inch cell for detection limits are less than 5 nanograms per liter. Bit of software review. So the method tab, if you click on the bottom, method tab, then expand what's in the box, you'll see the method controls, and that's the user interface for method controls. Here you can change the gas flows. You can monitor the gas input. You can move the auto sampler probe, or I'll refer to it as ASX probe. You can change pump rates, inspect detector lamp outputs, and run standby routines for the end of the analysis. This is great for method development. So the gas flows, you can set from 0 to 1 liters per minute. Your usable range, however, is approximately 0.15 to 1 liter per minute. And that's just a drop-down menu, and you just highlight it and then close it. You can move the probe, move it to the rinse, up for air for shutdown. You can move it to the standards, to the samples. You can start your strip chart recorder and send it to a sample. This might be advantageous in method development. Pump rates. So the pump rate, 2 to 11 mils per minute is the settings. Typically, most methods would run at 5 mils per minute. So if you increase or decrease with the gas and the probe time in sample, that's going to adjust the dynamic ranges. So those 3 items, the gas flow, the pump rate, and the time in sample is your basics for method development. Under the calibration tab on methods, you can choose your fit, spec calibration. You can remove points by highlighting and unchecking the replicates, and then that calibration point will be removed. And on the upper right, you can change your fit from linear to quadratic and also weighted linear. On the Standards tab, you can add, modify, or delete standards. It's really easy. Select the number of integrations. You can run normal or MSA. MSA stands for Method of Standard Additions. Also, adding standards, modify, you choose it, modify, and save. Add a standard, enter the name, concentration, units, and save. It's that easy. And then you can also delete standards here. So basically, on the Methods tab, and then when you highlight what's in the box, that's the basic information for running the system, method development, setting your quality control, and so forth. So on the Quality Control tab, this is where you add, modify, delete QC standards. You can also choose type, check, spike, or dupe. And then you can set your target range, so absolute or relative. Absolute is a concentration. For example, if you had a 1 ppb standard and you wanted absolute at plus or minus 20%, you would choose 0.8 and 1.2 for the concentration. Or if you wanted to do plus or minus 20%, then you just choose relative and use 20 and 20 for the high, and it'll give you the same thing. It'll be 0.8 to 1.2. QC automation. So you choose your automation, you choose your standards, and you set the cup position. Over on the right here, we set the cup position. You can choose the QC. You can set cup positions up above, and then you can set your actions. So the actions would be continuous examples as continue, stop, and repeat. So how do we set cup actions? Just drop down menu and you pick your cup. You have your choice within the system, or 12 to 16 positions for the standards rack. It ships with the default of 12. And if you want to change that, you would have to have a different rack, but then you change it from tools, auto sampler, controls. In tools and auto sampler controls, now you also have the option to change your rack size. So the rack size can go from 8 to 50 mil tubes, and that'll give you samples of 270 to 63. So for example, 63 tubes, that is 50 mil positions. Standards rack, as I said, 12 or 16. The default is 12, and it gives you 2 large volume positions for quality control. Analytical parameters, this is the last subset under method. This is where we set our integration time, and replicate integrations. Also your rinse time, uptake, limits, which is for your calibration. It'll bracket the samples that are below or higher, it'll flag them. And then dilution correction and method notes. And this is all on the analytical parameters. Software review of the method menu. So please note that on the bottom of this dialog box you have method, sequence, and analysis. Whichever one that you're checked on, the drop-down menus for view, run, tools, and help, they don't change, so they stay the same. So on the drop-down menu, if you're highlighted on the method, then you have open, new, rename, save, and clone. Clone's a nice feature because it'll take a method and duplicate it, and this could be used for method development. So if I want to add a standard or delete a standard to expand or tighten up my calibration range, you just clone one and then go into add standards or delete standards and make that change, and then uncheck or check those boxes on that field. And then of course you have exit. Sequence menu, when you hit that, you have new open, save sequence as a .seq file. That's kind of nice because if you save a sequence, let's say you're running the same type of sequence all the time, you can save it and then recall it, and you don't have to type in those samples. Maybe just change the names a little bit. You can print. That's kind of nice for taking the sheet of paper over to the fume hood so you can load samples and reduce mistakes. And of course you have exit. On the analysis menu, when you're on this menu, the reports show up. This is where the concentration fields and all that from the standards and the samples will be. You have new set limits, report control, report type, report precision, and exit. So on report control, check them all, because if you don't have them checked, those type of samples and or unknowns will not show up in the report. Same with precision. So F is for decimal places and G is for significant figures. So just check them all, and then you'll, for example, G, you'll have 4 significant figures, G3 is 3, G2 is 2, and so forth. On the View menu, you have all chapters, latest chapter, and date range, sort. So if you're looking for something, just go sort by date, and then you can choose the chapter and open it up, and you'll see the results. It's a nice feature. On the Run menu, we have standards, QC sample, method of standard addition sample, sequence, stat sample, and stop. Now the standard QC sample and method of standard addition sample, those are manual type modes, so it's going to ask you to move the probe. So during method development, I don't use those. I have a little trick I'll show you. It makes it a lot easier. Stat sample, if you're running a sequence and you click stat sample, it will prompt you to load it in the 3rd rack and the last position. And then if you click go, it'll run the sample, and then it will go back to the original sequence and continue. In the Tools menu, this is where you have some troubleshooting options, your data management, and some user functions. And then also there's the Help menu. So you have Help, and then the Startup file, which is an initialization file. It's startup.ini, and that's just a simple format for giving some commands to the software. And we can change some of those commands, and it gives you the command set in the startup file. But I urge you not to change any commands or do anything unless you check with service or product management. And then also about Envoy, we'll give you the software number. Let's move on to the Sequence tab. So in the Sequence tab, that displays the current sequence in the queue. Your standards rack, now they're numbered from front to back. So the lowest standard is out here 1, and this is a 12 position rack, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the samples are numbered from back to front, so they come this way. This is a nice setup. So typically you would set your lower standards to a lower number. So in case there was any type of drop or dribble that would come off the sample probe, which is unlikely because it's Teflon, it would not fall into a lower standard. So if you're running quality control samples, you definitely would want to have your lowest quality control up front in 5 and your higher quality control concentration back in 9. Sequence changes. So that's pretty easy. You can navigate to the QC automation page. You can check desired standards or QCs. Samples you just highlight in the sample cell, and then when you're on the sequence page, you just click update, and it'll update that sequence. So if we go back one slide, right here I'm setting up some quality control during the run and at the end of run, and then I updated the sequence, and it shows up as end after the calibration and then end of the run. So that's why there's 2 in there. I don't have any samples. So then to get some samples, you just place the cursor in the desired position and type. Sequence options, you have fill down, copy, paste, cut, auto number, and then you click update. So now I added some samples and I updated, and it filled in the sequence. And if you notice in the dialog box here, it shows all the standards and then the quality control at 10 samples, and then at the end of the run we also have the quality control again. Now let's say that I want to auto renumber, so you just click on the auto renumber, and set an integer. So how it works is the samples will auto renumber as 1, 2, 3, and so forth. 2, it'll add 2, 3, it'll add 3, 4, it'll add 4, and 5, it'll add 5, and so forth. And then it will automatically renumber those tubes. To do the fill down, you just highlight the cell that you want, and then keep your left mouse click down and drag it down, and it'll highlight those boxes, and then it'll fill it in. Same thing for cut and paste and copy to clipboard. And those are all the features right up here on these little menu buttons. So you can also add an intermediate QC, and it's very simple. So add the C and cut position. So enter the desired QC, refer back to QC automation, so you know exactly what standard you want to enter, and then under the cup action you just type a capital C and that position, and then whatever you set for quality control, it'll follow that sequence. And as you notice, when I updated, it added those 2 quality controls because I said after this sample I want that, and it put it in there. Startup. So that was the conclusion of the quick software overview. So startup, let's do this. Let's inspect the pump tubing. Remove the pressure clamps, and you want to feel the pump tubing for flat spots. If you have any flat spots happening, or it looks like it's starting to wear, just go ahead and replace the tubing and replace the whole set at one time. You want to clean and fill the rinse reservoir. HCl, nitric acid, is optimal. 5 to 10% HCl, maybe a 2 to 5% nitric. You'll just have to decide what works best for your method. You want to inspect the sample probe for any deposits on that tip. It's a screen tip, so if you have any, you can either replace it or soak it, or do a backflow flush using the pump. So you just rinse backwards with the peristaltic pump with some acid, maybe a 10 or 20% nitric. Next, you want to inspect the sample cells. Make sure they're clean and pristine, which they always should be. Inspect the gas line from the dryer module. Make sure it's not kinked or anything has happened. Maybe some water droplets from the dryer membrane that's starting to fail. Just make sure it's all clean and dry and ready to go. So you want to inspect all the tubing tees, make sure they're all connected and nothing's happened since the last time you run it. And inspect the gas liquid separator. It should be pretty pristine, shouldn't be white and full of gunk or anything like that. Start up, so open the gas valve on the gas tank, inspect the gas pressure on a regulator. 15 to 25 psi, 25 is max, I recommend about 20 psi. Connect the rinse line to the rinse reservoir bottle. Ensure the waste reservoir is empty, and click the startup icon. Set the pressure clamps on the pump. I use the 3 o'clock position. And again, make sure that you have clean rinse and fresh rinse and it's ready to go. So ensure the rinse station fills with rinse. You're going to look for like a convex bubble. That means it's not removing rinse faster than it's supplying it. If it removes it faster than it's supplying it, you may want to change the pump tubing on the rinse pump. If it removes it faster than supplying, you're going to have air voids in the system, and your signal will become unstable, and your RSDs are going to increase, which will also increase your method of detection. Next, you want to ensure that the drain lines are flowing nice and smooth. Ensure that the pressure sensors on the instrument user interface indicate that there's pressure in the system. And you're also going to see the bubbling through the gas liquid separator. Once this is all done, then you should be almost ready to go. So, method development. Now I'm going to talk about how to develop methods for your sample analysis needs. So basically, you have 3 things: gas flow, pump rate, and time in sample. So gas flows, high flows are going to equal short residence times, or the time that the mercury is going through the cell, and speedy results. But it's going to decrease the sensitivity. Low flows will equal to longer times in the cell. That will increase the sample times, and it increases the sensitivity. You have to balance these to meet your needs. So pump rate will increase or decrease time to the GLS and the mercury load. Sample time in sample, or time in sample, increases or decreases the sample load. Adjust to hit the steady state for a signal plateau. So if you adjust all three of the settings, you can achieve your desired results. So first we're going to look at a method from 0 to 1,000 nanograms per liter, or 1 ppb. So I'm going to enter in the standards and their desired location, but I'm only going to check the blank in the highest standard when I'm developing a method. And this will allow me to do a peak profile by using the system auto sampler and do it with automation, so I get the full timing of my system. So I'm going to see the probe move, the exact time it moves, and all that will be true to the system. So here I entered in standards of 0, 520, 100, and 500, and then 1,000 nanograms per liter. The 5, I'm not really sure if that'll work yet, but I'm going to leave it in and see what happens. When you become experienced with the system, method development will become second nature. So what do? The system's pretty forgiving, so don't sweat it. I'm going to start out with the pump rate of 10 mils per minute because I want to get it there as fast, and it's kind of a trace method. It's not an ultra trace method, but a trace method, so I want to have max load. Gas flows, I really don't have a clue, but I think maybe 4 liters per minute might get me what I want. Integrations, I know I need at least 2 seconds and 3 replicates, so I have a nice standard deviation. Rinse time, I'll start out with 30 seconds, uptake of 40, and always check the smart rinse. Have your smart rinse on for all methods. So I run the sequence. So I have to update the sequence, run my blank, and run my high standard. And I see the trace comes off. It's still rising, so I'm not seeing the full peak. So now what do? Well, I can change the gas flow and get it into the gas stream up to the detector faster. So I'll go from 0.4 liters per minute to 5 liters per minute, and then I run it again. The signal is now at a steady state. Sample uptake change, maybe. Let's see what happens. So let's go from 40 to 35 seconds, because on the previous slide it was quite flat, so I had more than what I needed. So then I changed the load. So now there's not as much mercury into the system, so the signal decreased slightly. But it's got a nice peak shape. The blanks seem to be normal and steady, so I think I'm ready to go. I need one more check. Let's read the low standard, see if we can distinguish between that and a blank. So over here, I do have the 5 nanogram per liter, and as you can see, I do have a single signal for it, although it's slightly low, but it is there. So let's navigate to the QC automation and check all the desired calibration standards we want to run. And then go back to the sequence page. They should be loaded, and then we can run that calibration. So all the signals seem very nice and stable. I ended up with a nice correlation with this method, 5 9s and 6 6, but trust but verify. So how do we do that? We're going to read back some of the standards and check them against the curve. So uncheck the QC automation, because if you don't uncheck them and you run a new sequence, it'll do the calibration again. So I navigate back to the QC page on the method user interface, uncheck those standards, and then enter the readbacks as samples. And I like to mix it up a little bit. So 500 nanogram per liter, blank in 20. And then I click update and run the sample. So the 500 came back at 522, that's okay. Blank came back at minus 23.7 or 24 nanograms per liter. So what am I looking at? So that tells me the negative blank, I'm going to have some type of carryover problem, so I need to fix it. And then the 20 came in at 22 2 nanograms per liter, so that's okay. So the method's almost set, but I have a blank issue. So anything below a 20, you wouldn't be able to report those values. So repeating the carryover test validates that I do have a problem. So now what? Well, let's increase the gas flow. Should get through the system faster, help with washout. I can also increase the rinse. Right now we have a 3% HCl, and the standards are also in 3% HCl. So should I increase it to a 2% HCl, 5% nitric? Not really sure. So let's try this. Let's change the rinse to a 5% nitric and 2% HCl solution. So the signal decreased a little bit on the 1,000, and that's because of my load time and changed the kinetics. So the signal flattened out a little bit, and so that was spread out over the time range. The correlation was still 3 nines, but it was down from 5 nines, and very little signal for the 5 nanogram per liter. So now what? Let's lower the gas, maybe increase the uptake time, increase the rinse time. So if I increase the uptake time, I'm going to put more mercury load into the system. So let's look at 250 or 0.25 liters per minute. Gave me a higher response. Signal still not quite at a steady state, so I changed it to 0.3 liters per minute. Lower response again because I changed the resonance time, so I'm pushing it through slightly faster, but the signal is stable, and I removed the 5 nanogram per liter sample from the calibration. Over on the right is the method development for that signal on the 1,000. It's very nice and a nice peak shape. So here's my final method. Pump rate 10 mils per minute, gas flow 0.3 liters per minute, uptake at 50, rinse at 60. I'm still using a 2-second integration with three replicates. So I build my sequence already created, so I check the standards, calibration blank of, and then a 20, 100, 500, and 1,000 nanograms per liter. And for the rebacks, I go blank 5, 1,000, 2,500, 1,000, and then a blank again. I want to really double check the method, and I like to mix it up again because in the real world, when you run samples, the unknown, they could be almost any concentration. So you want to make sure that from high to low, you don't have any issues. So over here on the right is the setup for this sequence. So once it's done, correlation's back. 5 nines, 5 8, nice correlation. And my readbacks, if you look over here on the right, I have a line through the 1,000, and it's got a 0 concentration. I was about ready to run out of 1 ppb solution, so I stopped it and refilled it. And then to start again, I just cleared the samples that had already run in the sequence and unchecked the standards and this on the method UI, and then went and run the sequence, so it'll continue on. So you have to pay attention to what's checked and what's unchecked, otherwise it would have ran the whole sequence again, but that's how you can make it happen. So once that was all done, my blank came in at 2.1. The 5 was at 5.1, but keep in mind that it's after the blank. So it's a clean system. The 1,000 came in at 1,028. The 20 came in at 15.7, a little bit low off the 20. 500, 498, 100, 102, and then the last blank came in at 1.4. So the first blank slightly high, maybe a little bit of contamination from the 1,000. The last one reading after the 100. Less mercury in the system, a little better value, but that's overall that's not too bad. So the blank following the 1,000, again, like I discussed, shows a little bit of carryover, not a lot. The 5 following the blank had a nice response. It's not showing, but it was 102%. And then again, the 20 following the 1,000 showed a small amount of carryover at a 78.5% recovery. So over here, you can see where it dips down below the line. So it's just going to measure from the blank correction spot and was still kind of coming down to baseline. So the true baseline is probably down in here. So maybe a little addition to the rinse time would correct that. The 20 would come in a little bit better. So for discussion, the readbacks, the absorbance units are very comparable to the calibration. So the blank was a -6 and the calibration was a 9. The 20 calibration was 204 units. The readback was 170. But again, that's because it followed the high standard. So we have a little bit of negative value here. So here's the 20 from the readback and the 20 from the calibration. The signals are the same shape. So that's very similar. The 100 is 108 calibration. Response was, or the readback was 1022, and the calibration was 108. I have a typo there, sorry. Readback is 4938 for the 500. Calibration was 4977. Nice steady signal, reproducible results. That tells me the system's working very well. For the 1000, we were 9,091, and the readback was 1,183. So over the range of 0 to 1,000 nanograms per liter, the method exhibited nice linearity, but some additional adjustments could be made to the rinse time or rinse solution to bring that 20 nanogram per liter into a more acceptable value. So the rinse time could be increased to 80 seconds. That would take our total analysis time from 110 up to 130. That's still acceptable for trying to run calibrations of 0 to 1,000 nanograms per liter. We could change the rinse to a 5% nitric HCl, which might or should enhance the washout. And additionally, it's very important when you do this to matrix match those standards to the unknown, because the matrices does have an effect and it will change the kinetics within the system. So always matrix match standards when you're doing the method development. In my case, I'm just running a simple matrix of hydrochloric acid for development purpose here and to show you what's happening. So let's go into 0 to 100 nanograms per liter. So this is more the trace mode. And when doing trace mode, you should have a tight calibration which brackets the unknown. And to analyze concentrations below 20 nanograms per liter, I do recommend the calibration of 0 to 100 nanograms per liter. It's highly recommended. So follow the same process that we did in the previous one of 0 to 1,000 to dial in the system. So I did all that, and I'm going to save you the pain of going through that. So I ended up with my final method, 10 mils per minute of sample uptake. My gas was 0.25 liters per minute. Uptake at 70, rinse at 70, integration at 4 seconds. So it's a trace mode. So I want to have a longer integration time to make sure that I have a steady state for that signal to read the lowest possible standard and achieve the lowest possible method of detection or instrument detection limit or limit of detection. And my rinse was just 3% HCl. So I ran a sequence. The calibration's 5, 20, and 100, and my readbacks were 100 blank, 5, and 20. This signal for the 100 was very nice, very flat, long plateau. So I'm integrating for 12 seconds. So the start of the integration will be over here, and it'd read 3 of them. My RSDs were extremely nice. The 5 nanogram per liter had a nice signal over here, so it's easily discernible above the blank. Calibration results, 396210. That's not bad. That's okay for this type of concentration. My readbacks, 100 nanogram per liter was 105. The blank was 1.3. The 5 came in at 6.7, and the 20 was at 22. And I think that's acceptable. So But over this range, it had nice linearity. Total method time was 140 seconds. The blanks were acceptable for the standards. Maybe we could dial in a little bit better, maybe improve it some with a change of the rinse a little bit. But again, this method wouldn't meet EPA 245.7. The system is just not capable of doing that. That has to have a method detection limit, instrument detection limit, method detection limit of 1.8 nanograms per liter. We wouldn't be able to achieve that with this system. And again, it's very important to matrix match those standards with the samples for the method development. EPA 245.1, this is a normal type method, and a lot of laboratories or drinking water, wastewater laboratories would run this method. And typically they would calibrate up to a 10 ppb, microgram per liter. And this method can be set up for speed. But to analyze below 0.1 microgram per liter, I do recommend using a trace method, or maybe that method that's set up for 0 to 1,000 nanograms per liter, or 1 ppb. Again, you follow the same process. So here we have a 0.1. It's showing an absorbance somewhere below 300 units. So it's got good absorbance, but if you start dialing back the concentrations, pretty soon we're not going to have a lot of response there. So that's why I recommend using tighter calibration with a method change for lower standards. So my final method for this was I set the pump rate to 7 mils per minute. My gas flow is 0.75 liters per minute. Uptake is 45. Rinse is 30, so 75 seconds of method, so barely over a minute. That's pretty fast. 2 integrations, 3 replicates, and my rinse is 5% HCl and 5% nitric acid. So I load the sequence. Calibration is 0.1, 0.5, 1, 5, and 10 ppb. My readbacks, I set them up to read the 0.5 and then the 10 and then the 5 and the 1 and the 0.1 and then the blank. The blank is a nice steady signal, and the 1,000 or the 10 is a nice signal as well at 36,000 of microabsorbance units. So my correlation on this method was 0.9991795, so 3 nines, it passes, and most of your methods of this type require 995, so it exceeds that. My 0.5 readback was 0.462, that's not so good, and I'll discuss that in a moment. The 10 was 9.95, and then the 5 was 4.2. The 1 was a little bit less than 1, 0.87, and the blank came in at 0.03, and the 0.1 came in at 1.6. So the reason my low level and the 5 are off is because I had a malfunction on the pipette. So the pipette standard was slightly off the curve. Maybe the volume wasn't quite correct. But I decided not to redo it and leave it in to show you how important it is for calibrations. So going back one slide, if that calibration was off, we're still at 3 nines, which is acceptable, but it kind of skews the line a little bit, so it changes the intercept. So if it changes the intercept and skews the line, that's why my 0.5 isn't at 0.5 or closer, it's 0.46. And then it reported the proper value for the 5 ppb because it's a lower value. So that even though you look at the concentration correlation and you see a number, it may or may not give you good results. It may give you decent results. So always the fallback is to strive for at least 4 to 5 nines on any system. Try to get that correlation as close to 1.0 as possible. So over the calibration range of 0 to 10 ppb, the method did exhibit nice linearity. The total method time was 75 seconds. Readbacks were acceptable. We discussed that, although they're poor because of the 5 standard being slightly off. And again, it's very important to matrix match. This is the good one. So let's develop a method for 0 to 1,000 micrograms per liter, or 1 ppm, 1 milligram per liter. So we can easily achieve that by connecting the low sensitivity cell for high concentration modes. So the analysis or calibration of below 10 ppb is not recommended in this method. So you want to follow the same process of reading the highest standard in the calibration blank. And to recap, under calibrations, under the method UI, on the QC and calibrations, you only check what you want to read the sequence, run sequence, it'll go to that sample. So then you get the full timing of the method implemented, so you get a really true value on how it's going to perform. So connect the short cell. So we want to disconnect the transfer line coming from the dryer, and that's pointed right here on the left. So this is the transfer line from the Nafion dryer or the dryer module up to the high sensitivity cell, low concentration. Then you want to connect that transfer line to the in port on the short cell, depicted over here. Next, you want to disconnect the exhaust from the sensitive cell and connect it to the short cell. So on the right here, I'm showing the cell connections completed. Now you're ready for your method development. Maybe, not quite. Okay, so high calibrations need to modify the startup INI file. So that INI file, as I said earlier, is a simple file that has some basic functions to control some of the activities within the software. So navigate to C Envoy, because we need to change the overrange limit from a default of 5 up to 15. And again, that is in there to protect the system from saturation. So if you have a saturation, it's going to check the rise and slope, and it'll kick that sample out, and it'll throw a flag, so you know you have a problem. But in our case, we want to run high concentration, so we need to modify this startup INI file. So if the overrange limit is already entered, ensure that the value is 15. If you need to enter it, just go to the bottom of the command set and type overrange limit space 15. So no spaces in the word overrange limit, capitalize each word, then a space, and then save and close. So it'll look like this, overrange limit space 15 on the bottom of the command set over here in the INI file. Now you're ready to go. So now it won't kick that sample out, and we can do our method development. So final method. Pump rate I set to 7 mils per minute. I need to really flush this thing out in a hurry. I want to get the sample there as fast as possible. I want to have my shortest residence time within the cell, so I set my gas flow to 1 liter per minute. Uptake at 30, rinse at 30, integration is 1 second. Replicate time is 3. My rinse, I just know right away that I want to have a good flush out, so I'm going to use 5% HCl nitric combination within that system. So sequence. Also keep in mind that Beer's law, when you start to approach a half of absorbance unit, you get into the nonlinear range. So anywhere between 300 microabsorbance units, or 0.3 absorbance units, to 5 absorbance units, you start to hit nonlinear function. So in this case, after I ran my method development, my response was greater than 300,000 units. So that tells me right there that I might not be perfectly linear, and I'm in that area of Beer's law where it might be somewhat nonlinear. So I automatically went to quadratic fit. I have a blank of 10, a blank at 10, 100, 500, and 1,000 microgram per liter is my calibration set. My readbacks are 5, 1, 100, 10, 1,000, and 500. Here's my 1 ppm. It's very nice, steady signal. Over here, I got nice responses. I'm ready to roll. So the results from quadratic fit, of course, they're going to be high because you're running quadratic. And then the readback. So a blank is minus 1.6. The 1 comes in at 6.4. Now, the reason the 1 is 6.4 is the same fundamental reasons why the lower responses on the 0 to 10 because of intercept and so forth. Now, if you approach a straight line of 1.0 or the best quadratic fit of 1.0, then that intercept becomes 0 or at the blank level. So then you'd get a better readback. But that also affects the low end of the curve. So that's why I don't recommend in a method like this of running a calibration or a sample, reporting the sample that's, say, maybe less than 5 ppb. So then again, the 100 came in at 99.6, that's nice. The 10 came in at 8.9, that's more than acceptable. The 1,000 was 975, and the 500 was at 491. So over a range of 0 to 1 milligram per liter, the method exhibited a nice quadratic fit. My total method time was only 60 seconds. That is ray-ship fast. That is really, really a speedy method for this type of calibration and the concentrations I'm using. Readbacks are very acceptable. It's not advisable to accept data below 1 or below 5 ppb. So again, experimental settings. When I was doing this method, very quickly, I set it at 3 mils, 5 mils, and 7 mils. Over on the right, I didn't see a signal. I saw a signal, but it was still rising. But it wasn't that steady state. So the 7 mil per minute gave me a nice steady state with a nice flat plateau to read the sample. And again, matrix match. Basic shutdown. Place the stannous chloride in capillary into 10% nitric acid. You want to flush for about 10 minutes. This will keep things from precipitating out in the lines in the GLS. Disconnect the rinse uptake tube from the reservoir. Move the stannous chloride to DI water. Flush for 1 minute. Remove the stannous from the DI water. Let the supply lines flush to dryness. Raise the probe, turn the lamp and gas off, and if you're going to use it in the near future, not using it in the near future, just do a complete shutdown. And ensure the wasteline clears and the waste container is empty. Basic maintenance. Okay, the gas liquid separator is pretty robust, so don't sweat it. Daily shutdown of 20% should keep it clean. And remember, daily shutdown goes a long ways to maintaining the system. Sample probe or the sipper, inspect and replace or soak in 20% nitric acid. There's not a lot of maintenance with the system. It's pretty worry-proof. Pump tubing, you're going to inspect that daily. If it shows signs of wear, just replace them all. If the tension is set properly, the pump tubing should last for greater than 100 hours of use. It's Sanoprene tubing. It's very robust. But if you want to change tubing or you need to change tubing, I recommend changing all of them at the same time so they all have equal hours. Don't change one and leave the other because then you're just asking for problems. Cell cleaning. So some of the basic cell cleaning tips. You need spectrophotometric grade isopropyl alcohol, cotton swabs, disposable beaker, wear powder-free gloves, purity wipes, and lab disposal wipes like Kim Wise, K-Dries, and so forth. So disassemble the cells. Keep the parts orientation the same. So left side, right side, front cell, back cell, etc. If you mix up parts, you can change the baseline parameters and different things within the system. So just keep them all the same and clean them and reassemble them exactly how they came apart. And wear gloves when you do this. So you want to clean the cells first. So once you have those clean, they're ready to receive the clean windows. So you want to wash the inside with a wet-up swab. Use a dry, clean cotton swab to dry it out, and then flush with argon to clean out any of the fuzzies or any particulates that remain. So you want to make sure they're cleaned out of there. You can use a gas stream from the instrument to do this. Set to 5 psi so you don't lose anything that you're holding make sure the pressure is low. Clean the windows, use the same process, IPA, dry flush. Be careful when you blow them off so the windows don't fly out of your hands. And reassemble immediately after drying to preserve the integrity of your cleaning process. Don't place them down on anything, just put them right into the cells. And then place clean the cell assemblies back into AA. So to wrap it up, the Hydra AA method development is quick and easy, and the system has some amazing group of dynamic working range to meet all of your calibration requirements, your sample requirements, and so forth. So leading that into the next webinar, we're going to have a method development with M7600. So coming soon, webinar near you, detection limits less than 0.5 nanograms per liter, EPA 245.7 compliant, quick trace software, unique patented gas liquid separator. And with that, I thank you for listening.